we were talking about variance and the standard deviation on Friday, and I mentioned that doing this calculation is a pain in the neck. I don't want to do it by hand. It's just tedious. So if I'm in Excel, I can do it directly. Here is our J.D. Power analysis of defects per 100 vehicles again. And I notice that when I do the descriptive statistics through our data analysis, descriptive statistics, when we go through and do that process, we end up with this giant list of stuff. And fifth one down, I got mean and median and mode. Fifth one down is the standard deviation. Right below that is the variance. But notice that says sample. And there was a difference in the formula, whether I choose to do sample or population. The options in Excel, if I want to do a standard deviation, it's STDEV. That's what standard deviation is shortened to. But there are two different versions there. .S and .P. And the difference is literally whether or not we divide by n or n plus 1. The population is assumed to be complete. We'll divide by n. So that's the .P version. The sample is .S. So if I finish this out with .S and then give it all of the data we have, it generates the standard deviation that we see in the descriptive statistics, which means it assumed we had a sample as opposed to a population. If these were all the cars in the universe, then I could do the standard deviation for a population, .P, give it the same data, and get a ever so slightly smaller number. The smaller because we're dividing by a larger thing. As we see in the formula that we created last time, in the sample, we divide by n minus 1. Population, we divide by n. It's really the only difference there. And that's to adjust for the use of using X bar. But if I'm not in Excel, I have this thing. You can put data in here and do a lot of statistic stuff in here as well. I'm going to make up a smaller list. So let's create a list of numbers that we were using last time, right? We go back and grab our quiz score ideas where we were looking at mean and median and mode. Here we go. Here are my quiz scores from last time. We had Tom, who had quiz scores of 20, 40, 70, 75, and 80. And he had a mean of 57. Here's what I could go through, subtract each of those numbers against the mean, square, add, divide. I could do all of that. Instead, on my calculator, there's this button that says stat. Right here. And above that, it's a little hard to see on mine, it says list. If I want to put in a list of numbers, I hit second list. And it gives me a bunch of lists, right? Okay. That's where I want to put stuff. So stat. There's my edit command. So I hit stat to edit my list. Hit enter. There are my lists, and I can type these numbers into one list. 20, 40, 70, 75, and 80. There's my list. I want it to do the standard deviation for me. I quit out of this. Quit is above the mode button, second quit. And I hit that stat button again. That's where I just was. Why am I back? Because the middle column here says calculate. I want it to do the calculations. I go there. And lo and behold, right at the top of that is one variable statistics. This is our descriptive statistics pile from Excel. Hit enter. If it takes you out to the home screen and just writes one var stats, you have an older version of the software on your calculator than I do. We can still do this from there. We just have to tell it which list is our list, and that's L1. If you're on the home screen, you'll have to type L1. L1 is found above the 1 button in blue, so you'll have to use the second command. And then I'll just tell it that's where my numbers are. In some cases, where we have this huge list of numbers and we have repetition in those numbers, we could make a frequency and say this number appears 6 times, and this number appears 5 times, and this number appears twice, and this number only appears once, and then I could have a list of frequencies. In this case, I don't have a list of frequencies because each number only appears once. I don't have to do anything there. But if I put the frequencies in the next column, I could do that. All right, let's calculate. There's my average, 57. And there's my standard deviations. It's given me 2 of them. S and sigma. It's given me these as if it's a sample, the larger number, and then as if it's the population, smaller number. So you can do these in all sorts of different places and never, ever, ever have to do this calculation by hand. You think, therefore, I'm going to ask you to do this calculation by hand? You are sadly mistaken. I would be more than happy to have you do this calculation, but that just means I know you know how to work your calculator. So, questions? And depending on how many data decimal places are significant, that will depend from problem to problem. Page 112 has a chart where we go through the entire calculation by hand. If you're interested in seeing a very systematic way in which we do this calculation to write it all out, please take a look at page 112. Questions? Variance and standard deviation are always positive. Why? Promise, there's a really easy reason from the formula why these have to be positive numbers. I'm adding up a bunch of squares. Squares are always positive, or at the very worst, they're 0. And then I'm dividing by a positive number. I have to have a positive thing for s squared or sigma squared. When I take the square root, I get a positive square root. I'm done. The only way my variance or standard deviation will be 0 is if all the numbers are exactly the same. The only way you have no variance is if you really only have one data point hit as many times as you want. The units on these numbers, all 3 of these have the same unit. These were quiz scores. So the appropriate unit here is points, right? That means your average is in points and your standard deviations are in points. Variance would be in points squared, and that doesn't make sense in terms of the application. But the units on all 3 of these numbers match the units on the data. That means it only makes sense to compare standard deviations in cases where the units are the same. If I was going to talk about the spread of stock prices, I want all of those stocks to be traded in dollars. If I was talking about the American market, the New York Stock Exchange, versus the Japanese market, I'd have a big problem because Japanese trades are in yen. If I go to the European market, I'm in euro. Again, the standard deviation now changes, and as soon as my unit changes, I'm really in trouble. It's like comparing apples and watermelons. Not exactly proportional behavior. We can fix that, maybe. By the way, since the average corresponded to my balance point in physics, variance is related to moment of inertia. If we think about that balance point, when you put a weight on one end, it causes it to bend, right? Well, when I square those, that gives me how things spin around that fulcrum, that balance point. That's moment of inertia. So there's still a physical reaction to this. How do I fix this? So I can compare across categories. We can create a slightly different measure of spread called the coefficient of variation. And the coefficient of variation is found by taking the sample standard deviation and dividing by the sample mean. Oh, by the way, that's going to give you a decimal, ideally. But the closer the average is to 0, the bigger this is going to get. So we turn this into a percentage usually and multiply by 100. I don't want to use that X there. That looks like I've got two X's. Let's just write it like that. So for our quiz data, our coefficient of variation is 25.88 divided by 57 times 100. So in this set of data up here on the screen, my coefficient of variation is 45.4. 45.4 what? What are the units there? What was that, Felix?
Should that be the same units?
Actually, no, it is different, unfortunately. It isn't the same units still. But you're right, the average is in whatever units, and the standard deviation, those are in the same units, right? So don't those units cancel out? This actually has no units at all. And that means I don't have to worry about comparing yen to euro to dollar or apples to watermelons or whatever. I can compare things by this measure across categories because this is unit free. So if I were talking about measuring the variation in someone's, I don't know, let me pick a sport in general, times in the 100-meter dash, that would be in seconds. I could get an average and I could get a measurement of how spread out those scores were. And then I could go over to the broad jump and I could measure the average broad jump at the meet that day. And I could measure the spread on those. And I could see which group was more consistent. Because the closer things are, the more consistent we are being. The wider apart they are, the less consistent we are being. This, unfortunately, really only works with strictly positive data. because when my data is negative, that kind of artificially shrinks both the average and the standard deviation. The average much more so. And the closer my average gets to zero, the worse this fraction gets. Questions? So if I look at the mileage on my car and I compare it to the mileage on my neighbor's car, I've got a Civic. She's got the hybrid. Same car, hybrid Civic, gas Civic. On the hybrid, she notices she's getting 43.2 miles per gallon. And when we look at the last 10 fill-ups, the standard deviation is 2.2 miles per gallon. In my gas car, I'm getting 27.2 miles per gallon with a standard deviation of 1.9. These have the same unit. So I could say at first, it looks like I am a more consistent driver than she is, because my standard deviation in the gas vehicle is smaller. What are our respective coefficients of variation? A little bit of calculation, and we get
5.1 for hybrid, and then the gas round up to 7.
so in absolute terms, the gas car has a smaller standard deviation. But in relative terms, it's got the bigger variation relative to its average. So if we were just going to say which of these is more consistent, absolutely, this is the smaller number. But relative to the size of the numbers we are looking at, the hybrid has a more consistent behavior. Now you might be going, what the hell? All right, hang on a second. Let's change settings. Stop looking at gas. On page 116, problem number 27. We have 3 stocks. We have the average price for the last, I don't know what time period, for A, B, and C. And we have the closing price variability, the standard deviation in those prices. So if I look at the past, I don't know, month, which of these stocks has the smallest absolute variation? Felix? Yeah, that's the smallest number. Stock C has the smallest variation in absolute dollars. Yen, euro, I don't know which market this is on. But the stock price is only $5.75. Oh, it says dollars. I should know. Whereas stock A is trading around 24.50 at 25 bucks, and stock B is around 150 bucks. So what's the coefficient? Relative to the size of the stock, which of these is the most variables? Well, let's take a look. I need to work out my coefficients of variation. So for stock B, the coefficient of variation is 12.25 divided by 147.25, multiply by 100, 8.3. What were the other two? I mean, that's pretty low. Give me the other two. Aha. 2.08 divided by 5.75. Yeah, it's got a 36.17 when I move the decimal place. So the one that we thought was the smallest in absolute terms has the largest coefficient of variation. The middle one, stock A, is 20 something. So I can't just look at the absolute number. If I was using stock C for my portfolio value would be all over the place, wouldn't it? But if I'm using stock B, then I have a relatively steady, in spite of the fact that there are large swings in the price per day, it's not a large relative swing. Questions? The standard deviation is based on the mean. So my choice of center decides that I am going to use this instrument. Since I'm using the standard deviation, my coefficient of variation, those go together. They are all based on the idea that I'm using the mean for center. Question. You go to the store to buy bananas, and you come home with a dozen bananas. Would you rather have a small standard deviation in size or a large standard deviation in size? Would you rather have a small average size or a large average size? And how do those affect each other? This is going to depend on how you like your bananas, right? So let's put that aside for the moment. Let's think about this. Emma?
I was gonna say with the bananas, you want a large standard size and little deviation.
Okay, so a large average and little deviation, and then the bananas will be the same. And I can eat all dozen bananas. Oh, that's gonna happen. But yes, they'll all be the same, right? If I knew I was going to parcel them out over time, maybe I'd want them to have a large variation. So some are very ripe today and some are not very ripe. But if I was talking about variation in size, well, then I would have some very small and some very big, and I don't know how that would taste necessarily, right? You are producing steel bars to use as rebar in a building. You have to hit particular diameter. If I know that's the diameter I'm aiming for, would I rather have a large standard deviation or a small standard deviation with an average that's wrong? Let's say I'm aiming for a 1/4 inch. But when I start making the bars, I keep getting 0.26 inches, not 0.25. Does it matter? Well, yeah. Bottom of page 117. These two pictures are about punching holes. The picture on the left shows that we are getting on average the 5 millimeter hole we need. The average of our target is right where the peak of our distribution appears to be. But there's a lot more variation compared to this red curve. This histogram shows a lot bigger of a spread, right? What happens with these? Well, if my hole's too small, I can't fit the thing into it. If my hole's too big, it rattles around. So these might get rejected. Whereas over here, the distribution's the right shape, but it's in the wrong place, isn't it? I'm consistently getting too small of a hole, but the variation is good. So we have to balance variation and center. A long time ago, might even have been last millennium. So in the late 1900s, I went and watched a shooting competition, military sniper competition. I would like you to think about this. These people were shooting weapons. The diameter of the bullet was 0.3 of an inch, roughly. They were shooting them 800 meters. Which would you rather have? A bad average and a good standard deviation, or a good average and a bad standard deviation? So if I have a bad standard deviation, it means one shot went way over there and one shot went way over here. But on average, they're right in the middle. So 3 statisticians go shooting. They aim for a deer. The first one misses 5 yards left. The second one misses 5 yards right. The third one goes, hey, we got him. Because on average, that was 0. But if I'm consistent, then all of my target shots will be in the same spot. And all I have to do is adjust my sight. They actually judge the competition, not by average, not by score, but by how tight the grouping is. The winner put all his shots, all 5 of them, within a $50 sized ring. At 800 meters, he put 5 shots. With something just a little bit bigger than that. He was, by the way, up and left on all of his shots, but damn, were they close together. That was a plot point in a movie. But I didn't see 3 bullet holes. I only saw one. Yeah, he hit exactly the same spot 3 times. Questions? Another thing we can do is to use that coefficient of variation idea, but do it to all of the data individually. To standardize our data. We're going to take our data and move it proportional to the average and the standard deviation. Now, this is individual. So I would have the first data point, the second, I'm going to call this xi. And each and every one of my data values gives me now a new number. I'm going to call this number zi, lowercase z. My standard deviation tells me how far away from the average I am. So what I've done here is I've said, oh, take the number you're looking at, subtract off the average, and divide by the standard deviation. And let's use that as a measure of how far away from the middle we were. Let's grab our data again from the quizzes. Compute, yes. So let me go back to our data for Tom. Let us standardize this data. These are the actual raw quiz scores. When I standardize my data, I convert all of these X's into Z's. Now, I can do that on here fairly quickly, one at a time. I can also do it with the list. But let me do this one at a time to start with. Clear that. I need those two numbers to be visible. 20, parentheses, 20 minus 57 divided by 25.88. There's my first z-score, negative 1.43. Repeat this with a 40. Negative 0.66. Now, as soon as I hit 70, I know these numbers are going to be positive. I'm bigger than the average, so the numerator here is a positive number, 0.50, 75, 0.6, I'll call it 0.70 because it would round that way. And then 80. Point 89. Do me a favor. Add up the z-scores. What is the total of all of these z-scores? 0. Every time. Give or take the round off errors, because I rounded some of these numbers, but I rounded and it worked out anyway. Because this represents how far we are from the average, and the position the average is balancing all of these things, the stuff on the left, the negative side, has to exactly balance the stuff on the right, the positive side. Now, the reason I want to think about standardized data comes in two rationales. One, a mathematician by the name of Chebyshev came up with a result that talks about any distribution of data and how it relates to the standard deviation. You had a question, so before I jump.
I did.
So talk to me. Stat, edit. So there's my list, right? I'm going to go up here where L2 is. So move over to list 2. And down there at the bottom, there's a formula for list 2, right? Take all of the things in list 1, subtract the average, and divide by the standard deviation. Watch what happens. It generated the whole list, didn't it? You're welcome. If the lists are longer, I use that same formula in Excel, but I don't have to do the calculation of the mean or the standard deviation beforehand. I can say subtract, hey, the mean of all of these, divide by the standard deviation of all of these because I have those commands. Chebyshev came up with this result. For any data set, regardless of the shape, the percentage of that data that is within K standard deviations of the mean for K bigger than 1 is 1 minus 1 over K. Times 100 to turn it into a percentage. I beg your pardon? What the fuck? Oh, is at least. I forgot to write those words. At least. Okay, wait a minute. So I look at my data pile. I don't know, I haven't made a histogram, I haven't made a dot plot, I don't have any visual image right now. But I go and I calculate the average and the standard deviation. So let's suppose instead of having 5 quiz scores, I had a whole class at the University of Pittsburgh's quiz scores. I've got 150 people in algebra. I gave a quiz. Here's 150 scores. The average was 71 and the standard deviation was 10. Well then, what this says to me is that you can tell me roughly how many people should have a score between 51 and 91. Now, I didn't just pull 51 and 91 out of thin air. What is the z-score for 51? And the score, the z-score for 71, I'm sorry, for 91 is hey, wait a minute. I want to know between 51 and 91, I want to know 2 standard deviations below and 2 standard deviations above. How many dots should be in there? Well, according to Chebyshev, the percentage should be at least this number. 1 minus 1 over, I wrote k. I forgot that's k squared. Doesn't help if I write the formula down wrong. People, fix that. We need that square. Please put that square in there. Sorry about that. So this is my correct number down here, 1 minus 1 over 2 squared times 100. What percentage is that?
So
75%. Because this is 3/4, 1 minus 1/4, that's 0.75 times 100, 75%. Now, that's 75% of my students. How many actual people is that? Hundred and 12 and a half. I don't know how to do a half a person. Let's err on the side of caution. Call it 112. At least 112 people should have scores between 51 and 91. It might be a lot more, but the more scores that are in means the fewer scores that are out. In order to have the same standard deviation, if I have a lot more in, I need to have some really far outs, don't I? But if the picture is kind of nice, like that one with our histogram that we were just looking at on page 112, then I might be able to say more about this. But 112 is a minimum number. If I look at 3 standard deviations, I should get more people, right? Because 1 minus 1 over 3 squared, 1 minus 1/9, that's 8/9, that's 0.88888888888. Multiplied by 100, that's 89%. 3 standard deviations, 89%. 1.5 standard deviations. 1.1, I just can't use 1. Why can't I use 1 in this formula? One minus 1 is 0. At least 0% should, no, I can't. Of course people will be in there, but it's not helpful. So while Chebyshev was working on this for arbitrary distributions, a guy by the name of Gauss was looking at different distributions, different pictures. Carl Friedrich Gauss, I've forgotten the year, 1800 somewhere, started noticing when he took samples over and over and over and over and looked at things, what he noticed was the pattern looked very similar to a particular histogram. And the more samples he took, the more often he saw this picture. And he came up with a formula for this picture. This is the Gaussian distribution, or the normal distribution. We almost always hear of this with another name. Anybody know another name for this picture? The bell curve. The bell, right? But the bell curve has very particular behavior. This curve is symmetric. It's the same on the left as it is on the right, and it is centered at our average. Notice they've used the Greek letters. That's fine. It still works for our Roman letters. This is written in population terms, but it also applies mostly to samples. If you look at one standard deviation up or down, that's 68.3% of the data. If you look at 2, that's 95.4% of the data. If you look at 3, that's 99.7% of the data. When you have this shape, those 3 numbers give me the same information that Chebyshev did, but better. By the way, this means that any data value way up here or way down here that's more than 3 standard deviations away from my average, that's really rare, isn't it? Remember we talked about trying to define an outlier? I just came up with a definition. If your data is outside 3 standard deviations, 3 above or 3 below, that's what we're going to call an outlier. So if your z-score is bigger than 3 or smaller than -3, that's an outlier. Now I have a method of checking. This requires us to know that we have data of this shape. And that isn't always true. There are lots of other data pictures, and that's what Chebyshev said. It said it doesn't matter what the shape of the data is, my result still works. But Gauss requires us to know some more things. There's a sneaky way around this called the central limit theorem. We'll talk about that in chapter 8. I don't write down all the decimals here. So the stuff that is outside of 3 standard deviations only happens 0.3%. And that includes both the low and the high. So it's really rare to get that. If the absolute value of z is bigger than 3, zi, then xi is an outlier. Somehow, though, the stuff between 2 and 3 standard deviations, that looked really small in the picture also, didn't it? Between 2 and 3 standard deviations, those are these little pieces, right? Those are pretty small as well. So if you're in there, that's pretty unusual. Let's use that as a definition. If absolute value of z bigger than 2, then x is unusual. This is particularly useful in data sets with a large number of things in it, hundreds, sometimes even thousands. The more data points we have, the more likely this is to be useful. By the way, I can use this to estimate the standard deviation. If 99% of the stuff is between 3 up and 3 down, then the highest and the lowest should be 3 up and 3 down. I can approximate the standard deviation using my range. But again, this assumes that I have a Gaussian distribution, a normal curve. On page 119 and 120, there are a bunch of calculations switching between z's and x's. We should be proficient at this. In the JD Power file, you'll see one of these. Here it is. One that says mean and median. hey, look at that third column, fourth column, where it says z-score. I did exactly this calculation right here. There's even a command built into Excel that says standardize. Standardize this set of data using the average and the standard deviation from that set of data. So I don't have to do this by hand. Questions? All of this is predicated on the idea that we are using the average for our center. What if we're not? Talk about that one on Wednesday. I'll see you then.